I'm going to give you the example to find the domain and range of the function of two variables. We have the experience to find the domain and range of function of one variable. We're going to apply the same one, the same idea, same theory for that one. And we've seen we have the under root sign, then our function g, as I mentioned above, that g must be bigger than or equal to 0. In this example, we're going to discuss the domain of the function. The function given to us is fxy and the root sign 9 minus x squared minus y squared. As I've seen above, when you have the under root sign function, then we take that function must be bigger than or equal to 0. Because under root sign minus will be a complex number, and that's not the real number. So we say the function is not defined. It's defined only when this is bigger than or equal to 0. So I put here this as 9 minus x squared minus y squared bigger than or equal to 0. So simplify this one, I take 9 to the other side, multiply minus. We get here x squared plus y squared is less than or equal to 9. So now we having here, because it's less than or equal to, we can say x squared plus y squared equal to 9, and x squared plus y squared is less than 9. Now this, this equation of a circle, and this is inside the circle. So this actually, if we say this one, this is equation of the disk. So you having the disk, and if this is bigger than or equal to 0, this is the equation of the hole. That is, the outside the circle is defined, the domain is not inside. Now when we say the domain of this one, that is the values of x and y, and we say the value of, when say x, y equal to 0, then the value of x is minus 3 and 3, and we take x equal to 0, the value of y is minus 3 and 3. So we having the domain of the function, all x, y points, where x is between minus 3 and 3 and y is between minus 3 and 3, and that's my circle. So then the other points, when we take here, any other point, for example, I have take here point, this will be 0, this will be on the circle, and here when you take less, this is inside the circle. We take here, for example, 2, so then x squared will be less than 5, this will be inside the circle. So here now we are going to take the graph of that one. What's my z? Because here this is bigger than or equal to 0, and here is plus sign. So this my z, or this function dxy must be bigger than 0. If I put this value function as z, so z is equal to 9 minus x squared plus y squared. I square both the sides. I get z squared is equal to 9 minus x squared and minus y squared. So then I am having here take the value of x squared, y squared right hand side. Then we have x squared plus y squared plus z squared equal to 9. And this is in principal equation of the sphere. This here I say this is my sphere, but we are having here the condition that our z is bigger than 0. This hemisphere. If this not condition is there, then this is the sphere. But as the condition is there, so is the hemisphere. And z is bigger than or equal to 0 is upper hemisphere. When z is less than or equal to 0 is a lower hemisphere. Is in lower hemisphere. If you take an Earth, the upper hemisphere is we are living in upper hemisphere, Pakistan, England, America. And if you take lower hemisphere, then we have here the countries like Australia and New Zealand and Indonesia. They are in lower hemisphere. Malaysia, they are lower. So we are having z is bigger than the upper hemisphere. So what is the range? Range is the value of z. So when we take here the value of x, y equal to 0, then z squared is equal to 9. The value z is plus minus 3 to 3, but minus 3 to 0 we are not taking. We are taking only z bigger than or equal to 0. So the value will be from 0 to 3. That's the, and if we want to sketch this one, this will be our base area, the circle, and here we are having all the points in this circle, because these are in the domain. And then we are having here the maximum value is 3. And this is my upper hemisphere, and solid one, because we are having all the points inside this one. That is in our graph. That's not the hollow sphere, but it's the solid sphere. So that's the idea we are having here in this one. And then we continue with the limit and continuity. In the calculus of several variables, actually we are just extended the ideas we have developed in the one variable calculus. So just extension of that one. Just something new we are going to do. What we have done in one variable, extend to two variables, extend to three variables, we can define the limit, continuity, derivative, integral. All of these things we can just extend it. So there is the rules we have just set for that one. How we accommodate more than one variable, that's we are going to define, we have to learn. But the basic formulas, basic definition will remain the same. As we are going to extend it to the limit of function of two variables, first we see how we did it for the function of one variable. Our function of one variable was y equal to f of x. And we say we want to find the limit of the function, f of x. When we say x is going to a, and the value of the limit is L. What are we saying? We're saying x is moving towards a. But x is not equal to a. X does not include a. When we see it graphically, so we're having here the value a, and we say our x is moving to a from left, while our x is moving towards a from right. So here we say this has a plus, and this we say is a minus. This is my x-axis. And then I have the value of this function. This, for example, here I just show it and make it this value. This is my y-axis, and this is my x-axis, and this is my origin. And say this is my curve. Now when x is moving toward this point, and then we are having this point is projected on z-axis, and this value of this one is L. So when it's coming from a minus 1 from left, it's moving from down, and a plus is coming from up. But the both sides is moving towards L, like this one is moving towards L, and here x-axis, y-axis is going towards A, this A. So we say we are going to discuss the behavior of the function near point A. Now again I'm saying not at point A. When this behavior at point A is same as the limit, then we say the function is continuous. If they are not equal, even then we say, I will give you the example that the limit exists, but it's not equal to value of the function. So that's the idea we discuss here. And here this thing we have done, we have the right hand limit. We defined it as right hand limit, and that's our limit is when we're having the limit f of x tends to, we say a plus from the right hand. And then we say this is equal to L1. We find here the left hand limit. Our left hand limit we defined here, and we say when we find this limit x tends to a minus f of x is equal to L2. Now we say the limit exists if we having the left hand limit is equal to a right hand limit, then we say limit exists. And we say, in that case, we can say here limit x tends to a, f of x is equal to L. Where what's my L? My L is equal to L1 plus L2. The same thing we can extend here. For example, I just give an example, simple example. Limit x tends to 2, we're having x square minus 4. When I substitute this limit, we just take the example here, x plus 2. Here we take here, they will limit x plus 2. So when I take the limit, then I get here 2 plus 2. The limit of this one is 4. So this here my example for that. Now if I take this same limit, and we say here limit, I want to find x tends to 2, and my function is x squared minus 4 over x minus 2. When I want to take the limit, this is 0 over 0. When I find here, substitute the values, it's 0 over 0. This means we have to do something more. We have to do some more steps to find the limit. We can't immediately substitute and get the result. So here we say do the algebraic simplification, or the second one is the L'Hopital rule. We take derivative of the f of x, g of x, and then we substitute the limit. I take here geometrical, that means we need some more work to do. We say limit x tends to 2, in this one the factor which is making it 0 is x minus 2, so get x plus 2 over x minus 2. We just simplify this one, and we can write here we have the function x tends to 2 is into x plus 2 is equal to 2 plus 2 is equal to 4. So we having this one, equation 1, and we say this is my equation 2. There is a difference between equation 1 and equation 2. In equation 1, the value of the limit, the value of the function is also equal to 4. When you substitute, the function is f of x is equal to x plus 2. When I take f of 2, then I have 2 plus 2 is equal to 4. So value of the function is also 4, and the limit of the function is also 4. But when we are going to take the second example, here the value is 0 over 0, undetermined form. And now we just find it, we don't find the value of the function. We find only limit of the function. And we calculate the limit. Here we say limit is 4. Not the value, we say limit is 4. Now when we say value of the function, here limit x tends to a, f of x is equal to L, and is equal to f of a, the value of the function. So here we say when this is the case, this is a very special case, value of the function is equal to the limit of the function, then this we say here, if this is the case, then we say function f of x is continuous at x equal to a. So what we have done? We have done three things in one statement. Number one, the function is defined. Number two, the limit exists. Number three, limit equal to the value of the function. That's coming in only one statement. Here, in this statement we are saying the limit of the function is equal to f of x. And left hand limit is equal to right hand limit exists. The function f of a is mean, function is defined, and they are equal. You see the function is continuous. So we extend these ideas for the function of two variables. Obviously, we have to do some more nice work, interesting work to do that.